on live. I'm just going to double check everything's going good.
Now it is. Okay, that's.
Why is it?
No, it's a bit floppy. Yes. It's live.
Wait, sorry, the other phone is, are you Secretary of CyberSec?
Yeah.
Max, can you speak into the mic and say like hello or whatever?
Hello. Yep. I'm just being.
Do you want a mic when you speak? Or?
I've got the lav mic.
Oh,
They're testing. Yeah, that's what they're testing.
All working, so you can start.
Hello. Welcome to our first student talk of the year. We have our first guest. This is Max Guppy. He's the secretary of UQ Cyber Squad. And today he'll be talking about IBS, I believe. Is that correct?
About what?
Wait, about what, sorry? Well,
RISC-V.
yes, RISC-V. And I'll let him take it away.
I don't need the mic. You all can hear me all right if I just talk like this. Cool. So hello. I'm Max. I'm a computer science student here, and for the past year, I've been writing a RISC-V emulator. It has been a very interesting experience. I've learned a whole lot of stuff about, well, RISC-V, of course, and about virtual machines in general, and that's what I'm here to share with you. So, first of all, yes?
Is that a flip a zero using the change of slides?
Yes. I was going to use my phone, but it had an unfortunate habit of flipping through the slides too quickly. So, first of all, if we're trying to make a RISC-V emulator, we got to figure out what are we even doing? So, RISC-V is a CPU architecture. Think a CPU architecture is just a set of instructions for how a CPU interprets bytes. My laptop runs on the x86-64 architecture. I see some of you in the audience have MacBooks. They run on Apple Silicon, that is ARM64. And RISC-V is just another CPU architecture. The difference, the real difference between RISC-V and anything else is that RISC-V is completely free and available for anyone to implement for any reason whatsoever. Unlike x86, where you have to pay a license fee to Intel, or ARM, where you have to pay a license fee to ARM. So, the general philosophy of RISC-V is that there's a small set of basic instructions that everybody has to implement, but then most of the advanced functionality is in a whole bunch of optional extensions that build on top of that base architecture. And we'll see a few examples of that through here. The main thing with the extensions point is that we need to choose what extensions we want to implement. And the ones we want to implement depends on what we're trying to do. So what are we trying to do? Me personally, I want this emulator to run Linux, which is a bit of a lofty goal for sure, but I'm sure it's achievable. The bare minimum set of extensions to do that is a 32-bit base architecture and atomic instructions. But to actually get that working, I'd have to compile the Linux kernel from scratch and build a whole initRD image, and that sounds like a whole lot of work. And frankly, can I really say it runs Linux if I can't just download a Linux image from the internet and run it on my emulator perfectly fine? So instead, I'm going to be running Debian Linux, which wants a few more extensions. It wants a 64-bit base architecture and all of these extensions. IMAFDC and Zixer, Zifensi, and supervisor mode. That's a bit of a mouthful, so we'll break it down and go through it step by step. The first thing we need is integers. RISC-V has 32 general-purpose integer registers, which are 32-bit or 64-bit, depending on the base architecture. And no, I lied. It's only 31, because the 0 register is hardwired to be all zeros all the time, which is useful for instruction composability, and it's generally helpful to have a 0 in a register whenever you need it. Speaking of, here are the instructions. I think there are 27 on this slide, but that's not really important. We've got just basic arithmetic between registers, we've got jumps and branches, we've got memory stores and loads, and we've got a way to interact with the environment. You'll notice in the architecture columns, there's no multiplication instruction, and that's because multiplication is a separate extension. That's the whole idea behind RISC-V's extensionality. It's designed to be able to be used on really low power embedded microcontrollers, but also be powerful enough to run on desktop systems or server racks. So Debian wants the multiplication, and they're very easy to implement on an x86 laptop. So there we go, integers and multiplication. Now, we could keep going down the unprivileged column here, but I'm actually going to jump ship and go over to the privileged ISA, because when you do the privileged ISA, you get access to a few tests. And it's very nice to know that we've implemented our instructions as planned. So let's talk about what privileged is. CPU privilege is a way to control the amount of things certain bits of code can do. Like, the web browser on my computer should not be able to read my secrets in, the web browser on my computer should not be able to read the memory of my Signal chats. That just shouldn't happen. And the way CPUs do this is by enforcing stuff through CPU privilege modes. In RISC-V, we have machine mode, has full privilege to do whatever it wants. Supervisor mode has a little bit less privilege, but supervisor mode then controls user mode, which is where completely arbitrary stuff happens, like your web browser and your terminal. Linux sits in supervisor mode in the middle, and we'll get to what happens in machine mode in a sec. But we have to implement this in our emulator, so it means we have to implement all the ways to restrict access to memory locations and restrict access to the CPU configuration registers, and we need to implement traps and interrupts. So traps and interrupts follow the same code path in RISC-V, and what they are is when the CPU executes an illegal instruction, or gets a new key from the keyboard, or gets a request from a user mode application to do something, or even has a regular timer interrupt, which is what Linux sets up. The CPU jumps code execution from wherever it was, anywhere in memory, to a dedicated trap handler, which then decides what to do based on what the trap is. The question now is, how is the code supposed to tell us where that trusted code path is? And that's what control and status registers are. They're accessed by some special instructions that we'll have to implement, CSR, read and write instructions. And there's about 20 or so that we have to implement right now, but I'm not going to go through all of them. I'll just list a few. There's mtvec. This is the one that I was talking about. This is an address in memory that the CPU will jump to when it gets a trap or an interrupt. There's also mstatus, which contains a bunch of single-bit fields or 2-bit fields related to these traps and interrupts, and also just some weird ones. Like, if you know what endian this is, mstatus contains bits to control whether supervisor mode and user mode are big endian or little endian. It can dynamically change between the two, which is a bit funky. You don't have to implement that, though. In fact, a lot of the stuff in here is optional, like MISA. when you read it, it tells you what extensions are implemented, but you can also allow software to write it and turn on and off particular extensions depending on what you're doing, which is kind of fun. Again, you don't have to implement this. You can just implement reading, and that is perfectly legal, and probably what you should be doing anyway for performance reasons. And then there's registers like mscratch. This is literally just a 64-bit wide register. Go wild with it. It's mainly for what happens when immediately after a trap you store one register into mscratch so that you have that register for use generally. So that's CPU. That's the first part of CPU privilege. We'll get to supervisor mode later. So now we can run the RISC-V test suite and verify that our integers and our multiplication are doing as they are supposed to. Then we can move on to atomics. There's two kinds of atomic instructions in RISC-V, and in most architectures anyway. There's the ones you'll all likely be somewhat familiar with. These are AMO add, AMO sub, AMO swap. This is a single instruction. AMO add fetches a thing from memory, adds one operand to it, and writes it back all in one CPU cycle. So like your fetch and increment is implemented in terms of this. But for more complex stuff, you might need to run multiple instructions between when you load the memory and when you store the memory. And that's what load reserved and store conditional instructions are. RISC-V is different to something like x86 in this respect, in that x86 implements a compare and swap instruction, but ARM and RISC-V use load reserved and store conditional. So that's what we'll be talking about. Load reserved and store conditional always come in a pair. See, second line here, we have a load reserved, then fourth line, we have a store conditional. If we have two store conditionals in a row, the second one will always fail. If we don't have a load reserved, the store conditional will fail. If we store conditional to a different memory address than we loaded from, then it will probably fail. It might be allowed to succeed if that memory address is close enough to where we loaded before. Yes?
When you say fail, do you mean like send the invalid instruction trap?
That's a good point. It will not fail as an illegal instruction, but it'll instead see that it has three operands. The A0 at the end is the address it's trying to store to. The A2 is the value it's trying to put in that address. And T0 is a destination. It'll write 0 to T0 if it succeeded, and 1 to it if it failed. But yeah, load reserved reserves the memory at location A0, and store conditional stores to that memory address only if the memory is still reserved, which is the pairing thing we talked about earlier, and if the memory hasn't been written to by another hardware thread or another device. Now, we haven't got any other hardware threads yet, and we don't have devices yet. So we actually only need to check the first thing. We only need to check that it's to the same address as a previous load reserved, and that there hasn't been another store conditional in between. So it is not as hard as the spec, very dense reading for this section makes it look. So with atomics out of the way, what have we got next? Floats. Floats should be easy, right? Like my laptop has a floating point unit. x86 has floating point instructions. I can just implement it with that, right? Well, not quite. See, there's these things called rounding modes in floating point architectures. And here's an example. Pretend this is a 5-bit floating point format. We have one number at the top adding to a second number down the bottom. That result, I forgot to fix that. But the result of this operation doesn't fit in a 5-bit precision. So we have to decide what to do with the leftover precision. We could round it up or round it down or round it differently depending on which one it's closer to. So RISC-V specifies 5 different ways for us to resolve this problem. We don't really care about what exactly they are as long as we can implement them. But that's the problem. We can't set these in high-level languages like Rust or Zig, or even technically C. It's probably undefined behavior, and and we generally don't want undefined behavior in your code. So we have to step one level lower. Not quite to assembly just yet, but instead to LLVM IR, because LLVM has these intrinsics which they're marked as experimental, but they supposedly let us add 2 floats with a specific rounding mode. So yeah, this is LLVM IR. It is not the prettiest language, and any compiler for it, well, no, not any compiler for it, but Clang specifically, which is probably the only compiler for it, to be honest. Clang specifically, if there's a syntax error here, it just crashes. It doesn't tell me where the error is, because I'm clearly not supposed to be actually writing this as code. But we can do it anyway, and we can compile it, and we can export them as functions to import, in this case in Zig. And then we can use those as floating point operations. Cool. Are we done yet? Well, not quite. We also have to deal with floating point flags, which are set in a special control and status register whenever an operation results in a divide by 0 error, or is interacting with NaN, or just has, or if we had to round for the precision one. So we have to extract that from our floating point unit somehow. In this case, on x86, this stuff is stored in a special control and status register called the MXCSR. This is not documentation about the MXCSR. This is a random Rust crate that I found because it was the closest thing I had to documentation on this thing. But we can get the value from the MXCSR with a special assembly instruction up the top there, stmxcsr, and we can put that into a variable and then extract each flag one by one, zeroing it out as we go so that the next time we execute an instruction, the flags register is all clear. And then we can load this back into the MXCSR with our zeroed flags with the LDMXCSR instruction, except no, we cannot do that. LLVM miscompiles this assembly instruction and causes a seg fault when it tries to execute it. So instead, we need to use another LLVM intrinsic to reset the floating point environment and call that as a function. Thanks, LLVM. Anyway, are we done yet? Well, no. We've implemented most of the floating point instructions, but here we've still got 4 more. We've got these fused multiply and add instructions, which, as the name suggests, they take 3 operands, multiply the first 2, and then add the third one at the end. The reason this is 1 instruction and not 2 operations is just because of the precision issues we mentioned earlier. It avoids a rounding after the multiplication and before the addition. The problem for us, LLVM only has fused multiply add. It does not have the subtraction and the negative multiplications. So I guess it is time for inline assembly now, or I guess module level assembly. So we can write our 4 functions for fuse, multiply, and add here. These are the x86 instructions for that. It's AT&T syntax, I don't like it. Oh man, we still have rounding modes to do. Okay, so rounding modes are probably also in the MXCSR. That seems to be where everything is. So if we go back to that Rust crate I'm using for documentation, we have 2 rounding control bits. And there's 4 different combinations of bits you can set for rounding modes. Wait, 4 different rounding modes? But there were 5 that we need to implement. So x86 implements an older version of the IEEE 754 spec, and RISC-V implements a newer one where they've added a new rounding mode. So this hardware just can't do that new rounding mode. But hang on, we've been using LLVM intrinsics for all of the other instructions. How has that been setting the rounding mode? It hasn't. It has just been doing the default rounding mode for every single thing. And at this point, there's 2 days of my life I'm never getting back. I caved and I'm just using a software floating point library. Sue me. Okay, with that fiasco, how about we just finish off the spec, shall we? We've got compressed instructions and we've got supervisor mode. So, compressed instructions are 16-bit wide instructions as opposed to the 32-bit wide instructions that has been everything else. And yeah, all of the instructions have been 32 bits wide up to this point, which makes them really easy to decode, both in hardware and in software. But it's not the best for code size, so there's 16-bit alternatives to some of them to make it kind of on par with x86 and ARM code size. So they're pretty easy. There's a few floating point instructions in there, but mainly just to load stuff to the floating point registers. So no pain. And then we have supervisor mode. This is the level in between machine mode and user mode that I talked about earlier. This is where Linux is going to run. And as being the place Linux is going to run, it is also where we have to implement virtual addressing, that address translation. I'm not going to go into the details here. CSSE 2310 has a section on address translation and virtual memory. But yeah, the important thing for us is that the test suite we've been using earlier with all the priv stuff has a nice VM for us to test our memory translation with, which covers some of the more weird aspects of the RISC-V page tables, including these accessed and dirty bits, which cause a page fault if they're not set, or you can implement an extension to set them yourself. So, glossing over all that, we have a RISC-V CPU now. Yay! This is, hey, but this is only step 5. I promised 10 steps here. We still have a whole lot of devices to implement before we have a virtual machine. Because, like, Linux can't talk to us right now, not from just this bare CPU. All it can talk to is, like, main memory. It can't talk to the internet. It can't even print us little characters onto a serial port because it doesn't have a serial port. So, yeah, how are we supposed to talk to a device like a serial port? Well, if you've done CSSE 2010, you will recognize this section from the data sheet. This is a table mapping physical addresses to hardware devices. In this case, GPIO ports or timers. The important thing is, regular memory load and store instructions, if you give them this memory address, don't actually access memory, but change the configurations of a hardware device. Main memory doesn't start until hex 100. And the same thing applies to big desktop systems as well. Like, this is the memory map of QEMU, at least in the configuration that I'm testing my emulator against. And only that orange region up there is main memory. The rest of it, most of the white is just open bus. If you try to load or store to it, it'll just it'll cause an access violation. But here we've got a big red PCIe bus. We've got a tiny green sliver for a serial port and a yellow sliver for a timer. But that's a lot of devices, and we can't implement them all at once. Not without testing anyway. What do we need to implement first? Well, we got to figure out how we're going to run this thing. So the Debian image I downloaded helpfully tells us a configuration of QEMU that will get it to run. And it gives us two pieces of software that it expects to run through. So the firmware, the thing that first starts up, is this thing called OpenSBI, which implements a supervisor binary interface API that is a RISC-V standard. This then boots into U-boot, which is a bootloader, and that is responsible for reading the disk image and booting Linux eventually. So I guess the first thing OpenSBI wants is a serial port to say hello to us and say that it is running. So that's the first thing we'll implement, serial port. But now the question is, how do we tell it where the serial port is? Is there a hard-coded address somewhere that we need to put it? Or do we give it information somewhere? The answer is the second. If we look through OpenSBI's documentation, it tells us how it expects to be run. It expects a heart ID in the A0 register when it starts up. That's easy. That can just be set to 0 because we only have one heart. Heart just means core in RISC-V language. And then in the A1 register, the second argument, it wants a device tree blob address. So what's a device tree? Well, it is a standard is a source format and a binary format for describing the layout of hardware devices in an embedded system or really any context whatsoever. It's consisted of nodes, like the root node and the CPU at 0 node here, and this interrupt controller node. And each of those nodes can have properties, like device type, or MMU_type, or compatible, which is a very important one. So we can tell it, hey, we've put a serial port at address hex 1000002000, and it's 100 bytes wide, and it's compatible with this model of serial chip, the NS16550. I chose that just because it's what QEMU uses as well. So it in particular is not very hard to implement. It's just a few registers that you have to read and write. Pretty much just writing a byte to this address will print it to the screen. And once that's up and running, hey, we have OpenSBI. Cool. So we've done that. And it will just go on to running through U-boot. So make a typo. U-boot is failing to boot. It is giving me an error code of -19. That means e-no-dev. It can't find some device at once. Okay. And the program counter is inside a function called showBoardInfo. That is a lie. The reason I know this is because, well, this took me a long time to debug. I had to implement the GDB remote serial protocol so that I could run GDB on my host system and connect to my emulator to debug the software running inside it. So with single-step debugging, I could search for that -19 from earlier and trace the source of it. Eventually, I managed to find it back to this function, RISC-V CPU get count, which, as the name suggests, gets the number of RISC-V CPUs that I've listed in the device tree. Okay, so why would this be a problem? Let's single step through it to find out. Okay, of node for each subnode. Okay, it gives us there is in fact a CPU node. We step through that. If not of node is enabled, well, our CPU should be enabled. I haven't done anything specifically to disable it, so step through that. Continue. Okay, so it isn't enabled. let's run that back and step into offNode is enabled. OffNode is enabled basically just calls this other function, fdtdec get is enabled, which, okay, let's single step through that. Cell equals get property status. I didn't write a status property on my device tree, so that should just be null. Okay, step through that. If cell, step through that. Returns to, oh, it isn't null. If I inspect the contents of cell, it says disabled. Disabled? I didn't even write a status property. Why is it showing up as disabled now? Unless, is this even my device tree that's being debugged? Okay, so OpenSBI, this is the address I gave it to my device tree that I wrote, and presumably U-boot expects the same arguments in the same order from OpenSBI. So if I put a breakpoint at the start of U-boot and read the A1 register, it's a different memory address. So clearly OpenSBI is changing the device tree for some reason. So okay, let's look through the OpenSBI source code to see where it might be changing where it might be changing our device tree. And we see this function called fdt cpu fixup. This is down the bottom of that particular function. It searches for a property called mmu-type. And if that property does not exist, then it sets status to disabled, which is, but hang on, mmu-type. That's definitely on my device tree. I showed it earlier, mmu-type. It's right here on the 6th line, mmu_type. This single character took me a month to find. That cost me my semester break. But we can fix that, and finally U-boot boots and gives us a shell prompt because there's nothing to boot from. Cool, that is progress. Now we need to give it something to boot from, and that thing is a virtual hard drive. We've been given a disk image by the Debian Quick Image Baker. It's just a raw image. But the question is not how to read the image. The question is how to expose it to the system. Normal computers usually use the PCIe bus and use protocols like SATA or NVMe to communicate with hard drives. But that's a proprietary standard, and it seems not very fun to implement if I can't read the spec. So maybe there's a better option? Hang on. What does QEMU do? That should be the first question. What does QEMU do? Okay, if I load the U-boot command line in QEMU, I can inspect the PCI bus with, well, the PCI command. And this is what it gives me. There is nothing on the PCI bus except for this bridge device, whose only job is to tell us what's on the PCI bus. So, okay, in that case, we should, well, it must be booting from something, so there must be some device somewhere that it can boot from. So we can use this command, dmtree, to tell U-boot to give us a list of all the devices you know about and their drivers. And we have a Virtio block device and a Virtio net device. Both of these it can boot from. So that leads to the question, what the heck is a Virtio? Well, the serial, the timer, which I didn't talk about, an interrupt controller, which I will talk about, all of these live in memory mapped I/O, as we've just discussed, which is fine. They don't require anything super complex. The serial port is just read this memory address, write this memory address, and it's one character at a time. It's easy. But for block devices, hard drives, and network devices, they tend to transfer a lot of data at once, and it would be really inefficient to do that just over memory mapped I/O. So it would be nice if they could have direct access to the guest's physical memory. And what would be really nice is if block devices and network devices had the same shared structure underneath so that I don't have to do so much work in implementing them. And that's exactly what Virtio is. Virtio is a specification for a whole bunch of virtual devices, not just block and network devices, but also a console device as a replacement for a serial port, and a whole list of them that I haven't memorized. And they operate under this one primitive called Virtues. This orange box here is the guest's physical memory, and that's the only thing that the device driver has to interact with from the guest side. It writes commands to an available queue, then the device picks those commands up, does whatever it needs to them. Like for a block device, for example, it interprets the command as a request to read or write, and then it just reads and writes from the guest's physical memory. No MMIO required. And then when it's done with the command, it writes it back to a used queue for the driver to then know, okay, it's done, this is how many bytes the device wrote, and now I can reuse this buffer for another command. So with that primitive, it is a little bit of a challenge to implement the device itself, but I'm not going to go too far into the details in this talk. And instead, U-boot now can load Linux from our raw disk image. And it gets to about here in the booting process, and then stops. What's it waiting for? Well, it's waiting for an interrupt. Because we haven't implemented interrupts for our serial port or for our block device or anything else yet. So we need to talk about those next. The RISC-V CPU has 4 interrupts. Well, technically it has 64 interrupts, but OpenSBI only exposes 4 bits to Linux to use. And those are software interrupts, timer interrupts, external interrupts, and counter overflow interrupts. Now, software and counter overflow are for very specific things. Software is for interrupts between 2 different hearts, which we don't have, so we don't use software interrupts. And counter overflow interrupts are for when the hardware counters, like the cycles counter, ticks up and overflows. And yeah, so we can't really attach any devices to that instead. So we're left with just the timer and external interrupt to connect all of our devices to. The timer is obvious; it can connect to the timer interrupt. But now we have three devices to connect to one interrupt source. We could just do that, but then Linux wouldn't really know which device the interrupt has come from, at least not without polling each one individually. So we actually, instead of that, we put another device as a middleman that receives the interrupts from the serial port, the block device, and the network device, and then triggers the external interrupt pin and tells Linux which of these 3 devices has actually interrupted it. The actual implementation of the device is, again, not too difficult. It just lives in memory mapped I/O. No Virtues or anything. But the interesting part is how this works in the sense of a device tree. So this is the device tree from earlier. I've cut out some of the stuff we don't need to see, except for MMU-type. That lives on. But we have the interrupt controller node now. We have labeled it with heart0_int, and we've given it the interrupt controller property so that it knows it's an interrupt controller. With this heart0int doesn't technically exist on the device tree. It is syntax sugar for an extra property called phandle. Each label gets all of the labels get different phandle attributes within the device tree, and it's just syntax sugar to make writing them nicer. In this case, our interrupt controller has a p handle of hex 1. So our timer that I did not mention we implemented, but we did implement it. It can just say it interrupts heart0_int with the two timer interrupt bits that RISC-V provides. There was only one timer interrupt bit I mentioned earlier. The reason there's two is because the two different privilege modes, machine mode and supervisor mode, have separate interrupt bits for them. And this desugars in much the same way as the other one, but instead of adding another property, that just inlines to the hex 1 that I mentioned earlier. The PLIC, the platform level interrupt controller as it's called, this is a thing that consolidates the interrupts. It is also an interrupt controller, but it also has the same interrupts extended property to heart0_int, this time with the two external interrupt bits for the two different privilege modes. And then our serial port and our Virtio block device, they can just say interrupt parent is the PLIC instead of the heart, and they can say which bit of the PLIC they interrupt. In this case, we just get to choose that arbitrarily. But yeah, cool. We've got an interrupt controller. So now Linux it's booting. So now we want to connect it to the internet. I mentioned the Virtio net device with the Virtio block device. They are very similar. Well, they are similar in the sense that they both use the same Virtio structure and a similar configuration structure in memory mapped I/O. So we can avoid a lot of code duplication by just relying on that. But the real problem with the Virtio net device is what kind of internet requests it gives us. It doesn't give us TCP, it doesn't give us UDP, it gives us raw Ethernet frames, which if you've done CSSE 2310, it also talks about networks. This is basically the lowest tier of the network stack. And it builds IPv4 and then TCP are built on top of that. So the issue with this is that all of our networking primitives in programming languages are designed to deal with TCP and UDP and ICMP at a high level and not just raw Ethernet frames. So we'd have to write a parser for that and a parser for IP, and that's just a whole, that is also a whole project in and of itself. So that sounds fun to do one day, but that one day is not today. So we're going to look at what QEMU does. It uses a library built for it called libslurp, which does all that hard work of translating Ethernet frames into ICMP and TCP packets, and which it then sends over the internet like a normal Linux application. It's not as straightforward to implement as anything we've done so far, because it expects to be tied into your programmer's event loop in a very weird way, using the poll system call and with some timers for IPv6 stuff. It's just a mess, and it's such a mess that I encountered memory corruption in the original Zig version of my emulator, so I had to rewrite my emulator in Rust to actually get it to work. But I eventually managed it, and well, what do? We've got a working emulator now. We can SSH into it if we use the libslurp special function to forward a port to the host system, and we've just got a Debian RISC-V system to play with. We can check the device tree because that's exposed via sysfs, which is really cool. We can see that It is indeed Rivet. I am not lying to you. This is my emulator, and we can talk to the internet. Here is uqcs.org over HTTP, because if I do it over HTTPS, it'll flood the screen. I don't want to do that. But if we can talk to the internet, then we can talk to GitHub. And if we can talk to GitHub, we can download my emulator's source code and run my emulator on my emulator. It's a little bit slow. Give it a second. And there we go. This is running the boot process that my emulator starts up in. This is OpenSBI, and it is going to boot U-boot now. I don't have a Linux image on the Linux image to boot from, but there we go. There's U-boot, and I think that settles it. This is a RISC-V emulator in 10 not-so-easy steps. I glossed over a lot of stuff in this talk. Does anyone have any questions? Yes?
I've only done video game emulators in the past, but do you have to worry a lot about timing in the specification?
Thankfully, no, because unless you're trying to make a cycle-accurate emulator of anything, there's nothing really that can go wrong with timing. Yeah.
But compilers aren't relying on cycle counts of RISC-V kind of instructions.
No, they're not. Yeah, I read about, what was it called? I can't remember, but instructions after branch instructions just to fill the pipeline cache. That is very cursed, and RISC-V does not have any of that. I will stop this output before it gets distracting.
A few questions otherwise. So why did you not go straight to assembly instead of using the intermediate representation?
I did not. I just didn't really want to write assembly yet.
Fair enough. And do you know exactly what was causing the seg fault when you were trying to compile that section?
Like, as far as I could tell, it really was just the fault of LLVM. It just wasn't able, if I get back to the slide, yeah, it was just not handling the register reference, the variable reference correctly, and it was pointing to an incorrect location on the stack. Really weird. Any more? Well, I think I'm done.
Thank you. Here's another mug to your collection.
Thank you.
That was very insightful. Thank you.
Thank you very much. Yes?
I know the answer to this, what I'm asking is, do you have a write-up for all of the stuff we talked about in this talk?
I have a write-up for the first half of it. The second half is coming. I've been bogged down with assignments and this talk, but it should go up on my website at mrcat.au at some point in the near future, when I have the time. But thanks.
So we have a piece. Oh, so do you have a question?
Yeah.
Are there any further steps that you want to be taking with this emulator? Are there any future plans that you have?
Yeah. Hopefully I can speed it up. You saw how slow it was before. It's 20 times slower than QEMU is, running the same Linux system. So I would like to speed it up. I'd also like to go through more of the RISC-V spec. There's like bit manipulation instructions and vector instructions that seem really interesting, and I'd like to implement those. I just haven't had a reason to because Debian doesn't use them.
And how long did this emulator project take for you? Like, cumulatively?
Well, like I started around this time last year, but in the past 6 months, I've been working a lot less on it. Mainly because I was dreading having to rewrite it in Rust. But I don't know. I don't have an hour count. I did not write a num hours function. Maybe I could have written a num hours assembly program.
Does anyone have any questions? Going once, twice? All right. Guess it's ready for PCL. We did overestimate, so you guys will have a really big meal today. Already. So can I also get the dietary requirement people to go out first? So vegetarian, vegan, and halal, and gluten-free.
Cool. Can I take this off now?